once you have enough battery. Okay. Today is our great pleasure to have Professor Tzu-Chieh Wei from Stony Brook University. Tzu-Chieh got his PhD from UIUC, University of Illinois in Urbana-Champaign in 2004. Then he was doing postdoc studies at Institute for Quantum Computing at Waterloo, and then moved to University of British Columbia before joining Stony Brook as a faculty in 2011. And now he's a full professor there. Today, he's going to tell us about his work on error mitigation in quantum computing. And Tzu-Chieh, it's all yours.
Thank you. Thank you very much for inviting me. It's really a pleasure. I have a second screen, but it's I didn't set it up very well, so I cannot see the audience, but I only see my slides at this point. And so if you have questions, just shout out and stop me. Yeah, basically what I would like to well, thanks the invitation from the group and also Professor Martin Savage. And so I like to tell you about work that I did with my graduate student Hong Ye. Can you see my cursor? Or maybe I make laser.
Oh yeah, that's much better.
Okay. So it's about efficient separate quantification of state preparation error and readout error, and also their mitigation. So let me just start very bigger picture. We all know quantum computers are promising and they start quite early by Feynman. You can simulate other quantum system more efficiently than classical computer using a quantum system. And of course, later Loy formulated universal quantum simulators. And important, probably the most important applications that we learned so far is Shor's quantum algorithms for factoring. And this task can perform exponentially faster than classical algorithm. And later Grover has a search algorithm, but the speed up is less, but it's more generic. And you could find more algorithm in this website, this quantumalgorithmzoo.org. I think it has over hundreds of algorithms. And yeah, if you're really interested into the detailed algorithm, you can find it there. And so personally, I'm interested in various models or framework for quantum computing. For example, the circuit model. This is most what people are using and most the NICS devices. And this also this topological quantum computations, adiabatic and measurement based. I'm interested in various computational models. And our current devices are still noisy, so classical coin the term NISQ, noisy intermediate scale quantum devices. And so a big milestone will be to demonstrate quantum supremacy or advantage. And there are a few notable experiments. For example, Google has these 53 qubit supremacy experiment in 2019. And as before, there is also the IBM's work on utility. So basically they declare now it's the utility age now. And I also learned about UW's work on quantum simulation of hadron dynamics in the Stringer model and using over 100 qubits. Yeah, so this is very recent work. I would like to hear more about that actually. But I also want to mention we have a previous work on simulating a spin chains on, for example, this IBM devices, Washington, up to 102 qubits just for the XXZ model. This is already in this work. And we developed a physics-motivated ansatz for this model, and we employ mitigations to boost performance. And we're able on the devices with the performance to get the energy within a percentage error. And so just illustrate this for the energy density, we could extrapolate to the thermodynamic limit that work agree well with the beta ansatz. And this is for the qubit XXZ implementations. So, okay, so the point of this, bringing this up is we use readout mitigation and gate mitigation. But actually there is an important ingredient that we have not considered is the state preparation error that is present in various superconducting qubit machines, maybe less so in other maybe ions or atomic devices. So in fact, I have not actually seen any work or substantial effort to mitigate this effect. It's likely that the error is small, but I think it's still important to have all the parts that can be mitigated and do that as much as possible. So this is the motivation that I bring up our work, and also why we're interested in this. So that's our motivation. So I want to talk, maybe just say a little bit more about noise and errors. And so, for example, the dominant one would be the gate error, because you spend most of time putting gates, operations. So this is the dominant part that the error comes from. And it is very important because as you want to run a large-scale simulation, the gate error amplified dramatically. And without quantum error correction, the problem coming from these gate noise and error cannot be completely solved. For the moment, we sort of set up with mitigation methods, and there are a few that exist here. So, for example, this paper by IBM, they propose two methods. One is the probabilistic way of mitigating it, and another one is doing these Richardson extrapolation. And there are also other work, including some of the method we use that they using the so-called gate folding or circuit folding, that many of them are already available in the IBM Qiskit software framework. And of course, there's also in discussions mitigating readout errors. We also have a work quite early in 2019, and we also tested on the IBM devices. And this has already, this kind of mitigation, readout mitigation has been discussed in various papers, and it's already a package in IBM. What's missing now is the state preparation error and how to mitigate them. And I feel this is less often discussed. Perhaps that's my view, is these many systems, the error rate is low. But I think it's still worth mitigating this and to see the actual performance after you mitigate all three types of errors. So that's the focus of my topic today. So I want to mention the state preparation and measurement. They usually called span errors. They are usually discussed together. In previous work, I list a few here. One of the work here is the so-called gate set tomography. Okay. Yeah. And our starting point actually is this paper that we found, Laflamme and collaborator in 2022. They proposed a method called measurement-based algorithmic pooling. The idea is very simple, is that this is a target state and you want to prepare, and you want to actually make it cool, in a sense, cool to the zero temperature to relax to the ground state. But at a circuit level, you couple to an ancilla and using the control NOT gate, and you measure the ancilla. So because if you really prepare this well in zero, the S1 qubit should also be 0. So what they propose is, let's measure the ancilla qubit. If it's 0, then we accept that. If it's 1, then we discard that. So this actually make the preparation error 1 order less. So this will be scaled as, let's say, delta square after doing that. And they say, okay, doing this many times, and you can drive, in principle, drive the preparation error to 0, to very small. Yeah. In this sense, once your preparation is perfect, then you can character the readout, right? So that's why they are proposing also you can actually characterize them separately. We based on this, so we provide a way to simplify it, and we put the paper on the archive. And as I was preparing for this talk, I found that they actually have a earlier paper, which they cited this work, but we were not really aware and reading the paper, and found out they have idea very similar to ours, but they came at first, but we recognize that they have some scheme proposed very similar to ours. But we also proposed, they didn't propose how to mitigate these state preparation error, but they do have a way to characterize a state preparation and read out separately. But I will describe what our view is. And also, we also did some experiment on the real devices. So let me maybe pause here to see if any questions. Okay, if not, let me move on to the next. So let me define what I mean by state preparation error. I'll mainly focus on one qubit, but then I can extend this characterization to all the machine in parallel way. I'll describe more later, but let's focus on one single qubit. And so you want to prepare the ground state or qubit 0's real state, and it's not perfect. And we're going to model the error to being there's mostly in 0, but a small probability delta SP is in one state. Okay. If you want to prepare 1, you would take this and apply the X gate to 0. And so this is what you get. So if you prepare 1, this is what we assume the error model is. But you may say, okay, this is not realistic. It could be a coherent superposition. But you can always apply a random Z. In a sense, it's called twirling. You apply a twirling by this Z gate. Then this Z gate, because it anti-commute with X and Y component, poly X and Y. So if you average the readout, the measurement outcome, in a sense, you are actually preparing this standard preparation error state. So in a sense, we can enforce the state preparation error to be of this form. Okay, so then I would forget about the coherent state preparation error, because I can by twirling then reduce to this form. So this is the form that I'm going to use in the subsequent discussion. So let's consider, for example, with these kind of errors, so 0 has some probability get flipped to 1. Essentially, this is a classical error. So 1 can flip to 0 as well with small probability. So you can write down a assignment matrix. So assume perfect readout. If I prepare 0, I have this probability to stay in 0 and delta SP, small probability to become 1. And if I prepare 1, this is my assignment probabilities. So if I have erroneous preparation, I have perfect measurement, I can ascribe this assignment matrix. I'll call it A. So, and this is actually how you could perform mitigations, but I'll talk more later. And usually this would be combined in the readout, but that may cause problems. Now, I would also mention that later, but just to talk about together with readout, let's assume the other limit where the readout is not perfect. So I can model the readout as two outcome POVM elements, M0 and M1, and I'm going to assume it's diagonal because I can also apply the twirling and then summing the statistics that effectively erase the off-diagonal element. But in general, its general readout is a POBM that has these off-diagonal elements. But you can enforce that to be this form. So in some sense, it also become classical. And this POBM element describe the probability of getting 0 will be you have some state, final state, and then you multiply this operator and take the trace. That's the probability of getting 0, right? And probably getting 1 is insert this M1 POBM element here, taking the trace. So this means that I also have some assignment matrix, assuming perfect state preparation. My zero state, it can be read out to 0, like here. But perfect 0 is a diagonal element 1, 0. So it could also have an error that being regarded as 1. So 0 can be regarded as 1 because the readout is not perfect. So similarly, a perfect 1 state has some small chain to be read out as a 0 and has larger probability to say 1. Okay, so this is like you have perfect preparation, but erroneous readout. And this is usually what people use to do the readout mitigation. If you apply the inverse to your readout distribution, then you can mitigate the readout error. But as you'll see in the next slide, that's assuming state preparation is perfect. So next slide, I'm going to talk about both state preparation and readout are all erroneous. So you have this assignment matrix for the state preparation, and you have this assignment matrix for the readout. So now we're assuming that they are all noisy and error. So, and the way to sort of compute what is the output is that you have these assignment for the state preparation, right? You have 0 can jump to 1. And because this is the classical process, this is essentially a stochastic matrix, you multiply the two processes. So you have these state preparation error, next followed by the readout. And this is really a simple calculation, and you found out that the final form of the matrix is very similar. It's 1 minus some error, small error, and this diagonal element is of that, and off diagonal element describing this error transition. Yeah. Any question on this? You could also, if you want, you could also draw a circuit with 0, and then the state would have 0 mixture with 1, and then you just calculate the trace of that state with the POBM, and you can get this matrix. Yeah, but I'm just using a sort of a convenient notation. You have state preparation and readout assignment combined together. You can also think of this as stochastic process. 0 get flipped to 1, and can also be flipped back because of measurement. But yeah, and this is the final output. I'm going to call this as span because it includes preparation and measurement. And so yeah, the detail expression is this. If you do the calculation, this delta span 0 meaning that the error of not getting 0. So this is my definition. We define this delta, these deltas are the error. This is the probability that you measure the opposite outcome. And you can see they don't add up. They don't add. So there's also the cross term. You have these deltas, SP, state preparation error, measurement error, but you also have the cross term here. So the question is, can I separate, and I do measurement and separate these three parameter. In general, I have three, the delta SP from the safe preparation. I have this delta M measurement. It could have different rate of error in 0 and 1. So I have three parameter, and you would say, okay, I only have two equations because the left-hand side is what I measure at the output. This is the probability. And there doesn't seem to be enough enough equation to constrain that. Even if you assume they are symmetric readout, you still do not have enough because they reduce to the same equation. So you see that to separately characterize the two error rates is not possible in just reading doing one qubit measurement here. You have to somehow couple to other qubit or environment or something else in order to determine, to provide more constraint. So I want to pause to see if any question.
I have a question.
Yes.
What's the reason behind assuming that the state preparation error is symmetric? Like wanting to prepare a 0 and getting a 1 versus the other way around.
That's a good question. So we sort of make an assumption that our X gate is perfect, or the highest fidelity is single qubit gate. So I prepare 0, then if I want to prepare 1, I just flip by using the X gate. So then you can make it symmetric. But I suspect you could also do some twirling with X. But of course, you have to assume X is perfect, and then you could get symmetric 0 and 1. So like here, in the readout, I could make these symmetric by twirling with the X. So at the end, I also have an X to sort of symmetrize the 0 and 1. But the rationale behind that, we make this assumption is we assume X is is really of high fidelity. The error is probably the smallest among all the gates. The poly gates are in some sense free for us and perfect. So that's why we have the symmetric state preparation. But if you have different mechanism to prepare 0 and 1, they may be different. So you have to trace how you get 1. Do you get 1 from 0? Right. So that's our assumption. Yeah. Okay. So let me move on. So that's the question. Is there a way to separate the two errors? You can also think of this intuitively. It doesn't seem to be possible because you prepare some state and you measure and you get probability. It's really an inner product of the two. Somehow, if you don't have extra process, this error here can be lumped to the measurement, and measurement can be lumped to preparation. Right? So it's not possible to separate if you don't insert anything else. And the answer is yes, you couple with the ancillary qubit. So that's what I'm going to show here. So the target qubit is what we want to characterize. And we're going to couple to the ancillary qubit. It's very similar to the scheme by Lin and collaborator. So we use C0. And for the moment, I'm going to assume C0 is perfect, but I'll come back to that to deal with the noisy case. So I'm going to have is target prepare 0, and in reality is going to have errors. And here I'm assuming perfect C0, and ancillary can also have error in their preparation. And I couple them and then measure 0 and 1 basis. And I'm also assume the measurement, the readout is also has errors. So I'm going to label the probability of measuring outcome that's not 0 as this symbol here. So 0 indicating I have error in getting 0. And here as well, the A indicate the ancillary here, T indicate the target, tilde here, the symbol here is, that's the one has the target at the CNOT gate. So we put a tilde here. So, and this second circuit is simple circuit. The difference is you have an X NOT gate. So in a sense, we are preparing one. So we're preparing one for the target. And here we measure to see the probability of not getting one, because ideally CNOT should not flip because it's control bit. Yeah, and here specifically you can measure the error not because we assume that if you have CNOT, you will flip if the state is 1, but if it's 0, you won't flip. And here we specifically interested in the quantity where we don't get 1. So I'm going to show you, it's really simple circuit. You can follow through with the errors version, and you can compute. So let me just show you the equation. So this delta tilde A0 span is what you measure here, and it's related to the span of the ancilla 0, span ancilla 1, and this can be measured. So let me just point it out. On the left-hand side, these are measured with CNOT, and the right-hand side are span that measure without the ancilla, and so without CNOT. You directly measure, just like previous case here. Yeah, you just measure directly, separately. So what this shows is that this is what I measured at output here, and this is what I measure separately, right? So if I have these two sides, the dash box, I already have these quantity, I can infer the delta SP, the target state preparation error. So these can be done experimentally, right? So you can then figure out delta SP for the target, and with also the span. So for the delta SP, you have the span, and you can figure out, you have two equations, you can figure out delta M0 and delta M1, right? If it's symmetric, then you only have one to solve. So you solve this linearly, and you can separately characterize a state preparation and read out error. Yeah, so this part, we just found out it was also discussed in the earlier paper, that they have same ideas. Then you could also ask the question, but I assume the CNOT is perfect. What if CNOT is not perfect? How do I deal with that? There are a few ways we mentioned that we can do. The most straightforward things is to use zero noise extrapolations. So I guess this is not a stranger to the group here, but let me just briefly say what it is. So suppose you have a gate U. It could be a sequence of gate or just a CNOT gate in our case. What we can do is by inserting CNOT and CNOT inverse, which is self. Okay, so you insert two CNOT. Ideally it's identity, but you can see how your measured quantity decay. So ideally they should have the same expectation value. It could be energy or it could be distribution. And you want to extrapolate to the limit where M is 0. So M is 2M plus 1. So this is counting how many U I apply. And you want to extrapolate to the limit where M is 0. And this supposedly is the so-called noiseless limit. And that's the essence of zero noise extrapolation. So I'm going to show you the actual experiment we did using the circuit that I show you here, really this circuit, and also separately measured. So, and this dot here is without gate stretching or gate folding. And here we have applied 2 CNOT and additional 2, etc. And you see this is the probability, and you extrapolate back. You extrapolate back, so you get 1 minus this delta span is about 94%. So this is what we measured on the left-hand side, because we have CNOT, so we extrapolate to the supposedly zero CNOT error. So we have left-hand side extrapolated, and we have the right-hand side in a blue dash box that they are measured separately without CNOT. So from here we can extrapolate delta SP. Yeah, so that's one way to deal with that. Yeah, so from here, for this here, because we measure qubit 10, and we extrapolate the target. So this is ancilla, and we measure the target. And we get the safe propagation error is about 4% on this particular qubit. And you could also reverse and treat 10 as a target and 12 as the ancilla, so you can characterize. So in a sense, if you sort of assign pairs of qubits, they are linked by a CNOT, then you can do these characterization in parallel. So of course I have to assume there's no correlated gate error, no correlated readout, no correlated state propagation. Assuming that's valid to the lowest order, then you can characterize pair of qubit. You only need two different set of experiment reversing the rows of the qubit that they play as target or ancilla. Then you can characterize this in parallel, all the qubit state propagation and readout all together. Yeah, for the entire machine. Well, we didn't do that. We only test for a small number of qubits. So what if I don't want to do zero noise extrapolation? Can I deal with the noisy CNOT? Yes, you can. And you have to assume some noise model. But mostly this is what people assume. For example, we're going to model the CNOT error as being ideal CNOT, but followed by independent poly channels. So I have ideal CNOT, and I have some poly channel. These P's are poly operations. So yeah, so this is, if you want to make progress, you have to make some assumption on the noise model. So what we're going to do is we will twirl the both qubit with poly, and anyway we do that to enforce the state propagation. But if we do that, then the Z gate when we average of these Z operation, the XY error, when they propagate, they become bit flip. When you propagate the CNOT through the CNOT, they become bit flip. They become classical in sense. So then we can assign effective readout assignment matrix A to CNOT. So we can assign something like this to take into account the error that the CNOT introduced. Of course, it's assuming the poly channel. Yeah, so this is like that. So, and then you can actually go work through the circuit. And for example, you would have CNOT apply, the error apply first, and then followed by the measurement error. So you can really characterize altogether using these, in some sense, the same formalism that we have. So the measurement would give you the state propagation error, and also the noisy measurement that include the C naught. So this is the circuit can be analyzed this way. So yeah, and here we also make a further assumption. We are assuming that when we swap the C naught control and target, we assume that it's symmetric, so the error sort of acts similarly. Yeah, this is the case if the channel has similar order magnitude of px and py, then you have this. Of course, we would like to get rid of this assumption, which I'll try to do that next. But let me explain using this assumption, polychannel, and then symmetric C naught error. How do we get the state preparation and readout separately? So these two are the circuit that we use. Very similar. Yeah, it's actually the same circuit, but now the C naught has errors there. And so you can still work through that. And this is what you get. So this is here, the noisy version with C naught. And this Q, the one indicating the one with you want to measure probably not getting one. So analyzing this, you see that the left-hand side is you measured. Let me just, you can measure this with C naught, and the right-hand side is measured without C naught. So then you have both can be characterized separately, then you can infer the state preparation. Okay. So yeah. So I already said this. So yeah. So then this is very similar to previous case, but we have made an assumption that is symmetric. And what you do is really you measure a noisy version, you measure without C naught, and then you can use linear equation to solve for the state preparation error. And once you have state preparation error, then you can figure out the readout. Here we assume the C naught is symmetric. Yeah. The next is one level more complicated is I don't want to assume symmetric C naught. So I'll see if I can explain this. But I would use the notation as D here, which I try to avoid using as D basically represented off-diagonal parameter. And as I said, you can do the compositions. So for example, you do the compositions. Here you say that you have a state preparation error, you have C naught noise, you have readout, and this altogether, this is an assignment matrix. And the assignment matrix of this form, my D symbol is just to extract these off-diagonal elements. So I'm going to write as this way. So what I'll need is I have these C naught, noisy C naught gate here. I want to have two of them, so I can try to extract the parameter of the C naught error, the C naught assignment. So this is my C naught assignment matrix. And so let me see if I could explain this. So let me explain this one. This one is the measurement here, okay? So it is composing with the state propagation error from this Q2. It propagated because of C naught. And it had the C naught error affected on this particular qubit, Q1. And then has the span error from the qubit 1 itself. This is the error that has no C naught there. So these are separate quantity. This is the propagation error from Q2. This is C naught error that affect the readout here. And this is the span error without C naught, without everything, just measured the single qubit Q1 here. So that's the equation. So in some sense, formally you can see this coming. And then let me see, this one is here. And you can see that this is it has a span here. You have preparation and readout, and you also have a CNOT. And if you work out, actually, you can combine the state preparation and readout together to have a span here. And this is the CNOT assignment, the errors coming from the affected on this Q2 here. Yeah, so there are details that I sort of gloss over because you really do it calculation you get this, but I'm trying to explain intuitively how you get this. So this one, yes, said yes.
So even though you write in this sequence, but in practical calculations, I mean, the order is not as shown.
Oh, so the order, you have to do the order, the state preparation, and then CNOT, and then readout. And you found out in these separate cases, these two can be combined.
I see.
These two, yeah. So that's through calculation. This is, I didn't show you the step.
I see. Okay,
yeah.
Thank you.
Yeah. It's not that you can arbitrarily combine, but the point is that, for example, if it's symmetric, if you have symmetric, like these parameters are the same, you can actually commute. If both are symmetric, you can commute.
I see.
Yeah.
I see.
Yeah. So what the additional thing that I have not explained is this one. So this one here has two CNOT, and because we have to use our, also we assume it's poly. So, and you see that because they are two poly, so there are two errors that apply. So if you analyze this, this output here, so you see that there should be also preparation error that come from, let me see, yeah, Q2. And but this, let me see. Because I'm measuring Q1. So there is this from Q2 CNOT effect here through this. So the Q2 would have some effect on the Q1. So this, and then this one is the effect on Q1, that squared twice. So you have to do calculations. So I cannot explain why I only have a Q2 here, a single Q2. Intuitively, you have, yeah. And at the end, you are measuring here. So you only have span from the Q1 itself. But I admit that I cannot explain on site why I don't have the Q2 to affect that. But it's really from calculations. But if you just look at the equations, the implication of the equation is that this is measured through the circuit, and this is measured separately, right, without CNOT. So then you count the parameter. There's this state preparation error from Q2. There is a CNOT error affected on Q1. This is affected on Q2. This is square of that. And this is the same as that. So there are only three independent set of parameters that you can solve. Yeah, so that's this here. So in a sense that you can do extra work to extrapolate the CNOT error, and then you can solve separately. Yeah. We have done the experiment. My student recently implemented this. he found out that the result is not as good as extrapolation. It's also not as good as assuming symmetric CNOT. So we don't know why. So it's likely the error model is not accurate enough because there might be coherent error. One thing we have not done is we could also add random poly to twirl the CNOT to make it not coherent. Yeah, but something that we plan we will do. Yeah. Okay. So this is I admit this is the most complicated slide to explain. Okay, so with all these complicated setup or explanation, but simple setup, I'll show you the one example we did on this Nairobi machine. This one has 7 qubit, and we can characterize all these. So you see that the state propagation is still percentage, like 1%, maybe slightly less 1%, but it's still of order 1%. And measurement, the readout is, it depends on the 0 and 1. So mostly transition from 0 to 1 is less likely, but 1 to 0 is more likely. So as you can see the trend here. And the span is, you don't separate the readout and state propagation. So these would be what you see from IBM device property. They will show you these. They sort of put everything into the readout error, but in fact, it actually contained the state propagation error. And this is what they use to do the mitigation. So once you have these parameters, you assume, in a sense, you are assuming perfect state propagation, and then you apply this to mitigate the readout. Okay.
Tzu-Chieh,
Yes.
can you wrap up in the next 10 minutes?
Yeah, sure. Yeah, I'm about to finish. Yeah. So yeah, so as I already mentioned, we can do parallel characterization for a large machine. So we only demonstrate here on the small machine. And you could also use different pair to check consistency. Yeah, so what I want to mention, maybe in the next 5 minutes, is I want to do comparison. So we can characterize separately the readout error, right? So then we can actually mitigate the readout error first. And once we have the readout error mitigated, then we can mitigate the error that's left is the state propagation error. So we're going to do that. So yeah, so let me, this slide just to show you that if you only have the span and then mitigate span without considering the state propagation error, what you get, the ideal measurement differ from what you do is there is a readout error that's there that you actually need to take into account. Yeah. So one question is there a noticeable difference or how to mitigate state propagation? I'm going to answer these questions in the next maybe 9 minutes. So state propagation errors, here I'm assuming I've already done the readout mitigation. So then the state propagation error include that you have ideal probability distribution. This distribution is assuming that you prepare the S1, S2, Sn. It could be 0 and 1 perfectly. And the state propagation error, remember, it's a mixture of 0 and 1. So the measured state propagation error after you mitigate the readout is really a combination of all possible ideal propagation. And these could be 0 and 1, and you really superpose that, you mix the probability distribution. So in a sense that if I have more information, so this matrix really is just coming from the state propagation error. And so what I could do is I could, so the left-hand side here is I am doing the state propagation error with all 0, but it could have errors, but I am measuring the output. Here, I want to run additional measurement with preparation, which could be in 1 state, 0 state, 1 state, etc., all possible combination, and I run this. And because I know the coefficient, how they mix, so you don't need to worry about the detail, really coming from the state preparation error. If you know all these, this, you know the coefficient because we already characterized, and this is really just a matrix. So you can solve a 2 to the n variable, and you can figure out the ideal distribution, which is all 0 here. So this is like, you could solve mitigate exactly, but it doesn't scale very well. Okay, so in principle you could do that, but we have a simplified scheme. We just want the error only at the second order delta square. So the idea is very simple. You just Taylor expand around this error point, and then when these error parameter being 0, it will be the ideal distribution, right? And this is this one with some deviation, some slope, and because of state preparation error and preparing 0 and 1 actually is linear, you could actually apply x and regard that is an error. So if I have a 0, I could increase the state preparation error by, sometimes I apply on purpose an x, which will increase my state preparation error rate. So then by doing that, you know the slope. Basically, this is you can get the slope from doing extra circuit with x. So the upshot is that we can solve this slope by additional measurement, so that we can correct and get a mitigated probability distribution. Okay, so yeah, so this may be a bit quick, but maybe in the discussion, if you have questions, we can come back. So the second question is there a noticeable difference to scheme of mitigate? So as I mentioned, we can separately characterize the state preparation and readout, but in the standard readout mitigation, they lump also the state preparation error into the readout and they do the mitigate. So is there a difference? So I'm giving you a simple circuit. This is initialize 0 and perform the RY gate on both qubit and do a CNOT. This is the output, ideal output. And the distribution, if I measure in the 0, 1 basis, this is what I get, the ideal probability distribution. And what I'm going to do next is I'm going to compute this standard readout mitigation and the mitigation that we have using separately the readout and preparation to see how good they perform. So this is ideal using the simulation. But here we can analyze for specific angles of theta. The standard method has the error of the ideal fidelity is still a first order 1 minus delta SP, as you naively would expect. But for our mitigation method, we get the fidelity accurate up to delta SP square, so it's second order. And of course, for special point, when theta equal to pi over 2, actually it's ideal because this is uniform. When theta is pi over 2, this is uniform superposition. In that case, both can mitigate back to the ideal case. So yeah, and we did a simulation for all the range of theta. This is our scheme. So yeah, this is our scheme, and this is the fidelity. The blue is the standard scheme. So they match here, but there is a gap here. There's a difference. There's a noticeable difference if you use the standard scheme or use the complete scheme. Yeah, so this is another example of 4 qubit The reason I show this because we have performed this on a real device here. This is Mumbai with the 4-qubit selected here. And we look at theta equal to pi over 5. So sort of here, because this seems to be a large gap. And so we perform the experiment. And so the standard mitigation give 99.9, and the one we have is 90.9. Yeah, it performed slightly better. The reason you don't see dramatic difference is that you see the state perfection error for these 4-qubit are small, less than 1%, except the last one. Okay. This is probably my close to my last slide. Is once you have the correct state perfection error and readout, then you can actually use them to do any experiment and do the mitigation. So we do the state flammography on this particular qubit that we used previously. This one has about 2% state perfection error. And we perform a state tomography. We want to see whether the state perfection error, is it coherent or incoherent? And this time we don't do the twirling. And you see, this is what we get, the tomography, state tomography. For preparing 0, preparing 1 is we have additional X gate. The trace rho square is close to the case that has these state perfection error being mixture, but slightly better than that. So there is some coherent error in their device. And yeah, so that's what I can say, because there's not much analysis. So let me conclude. So we introduce a simple approach to separate state preparation error and readout error. And we propose how to mitigate both readout and state preparations errors. The readout is really using the previous scheme, but with the correct assignment matrix. And the result more accurate if we mitigate also the state preparation error compared to just the span altogether. Yeah, so the future would be extend to correlated state perfection error, but although I expect that should be small. So with the separate characterization, single qubit, we probably get a dominant error, and then maybe what's left would be, there could be correlated state perfection error, but I would expect to be small. And also the correlated readout, this might be there more dominantly. So this paper that I found out this week, they also have some statement about that. I want to point out, they also discuss the noisy CNAT case, but their point is not to pinpoint exactly these parameters, delta SP, delta M. They give an error bar on the range. So yeah, with this, I stop here, and thank you very much for your attention.
Thank you, Tzu-Chieh, for the very nice talk. Now,
thank you.
Questions.
Should I stop sharing?
Please keep sharing.
Okay.
Thanks for this very interesting talk. I was wondering, in the context of fault-tolerant computing, what do you believe is the role of being able to quantify these state preparation errors? Because it seems like fault tolerance corrects basically gate errors, coherent and decoherent. But if I think of, say, preparing the surface code or something like this, I always start at 1 qubit and then see not my way through other qubits. So if that first qubit already is prepared incorrectly, then I'm basically. Do you think that's an important problem to look at?
Yeah, I think this is a very good question. Also, important problem. Yeah, because state preparation error, if it's large, then this will have consequence on whether it can be fault tolerant or not. Because mostly when we deal with this, we lump these. We can say the state preparation error is also a gate error. It starts with perfect preparation and then error error gate. And so then you perform the fault tolerance analysis that this has to be considered. And then with CNOT, it can propagate with these entangling gate, it can propagate, right? It would eventually become a correlated state perversion error, because with these CNOT, the correlation is created. So it can be an issue, but I also do not know whether anyone discussed this seriously. Yeah, but this is a very good question.
Yeah,
How to deal with that is maybe you could do these kind of mitigation, but I also do not know whether this can help the fault tolerance itself. The fault tolerance rely on the gate really is small. If the gate error is small than the error threshold, perhaps mitigating state preparation would help. So that's my naive thinking.
Tzu-Chieh, I also have a quick question. So when you talk about state preparation, I think in this talk you focus on the single gate error, but could the CNOT error be in principle part of the state preparation error, just as you show in some later examples?
So CNOT, we basically lump into the assignment matrix. So it's everything that we have, the language is the effect on your measurement. So we lump into the assignment matrix and we analyze that. So we don't regard CNOT as a preparation error, but you could, in the sense, it depends what you prepare. If I prepare 0, then my preparation error is a mixture of 0 and 1. But if you want to prepare a cluster state or torical, then that will be your state preparation error.
Yeah.
So it's where you cut the line. But we are looking at the error when you prepare the 0 state.
Okay, gotcha. Yeah, thank you.
Sure.
Any final rounds of questions? I see no more questions. Let's thank Tzu-Chieh.
Thank you.